Hello friends, I am T2 sir. We are here today to understand statistics. We will discuss the use of statistics to analyze large sample of data which is outcome or observations of a variable. In this session, we will answer 5 questions. The first question is, what is the frequency distribution of the observations or outcome of the variable? The second question is, what is the expected value of the variable using past observations? The third question is, how to define risk associated with the outcome of the variables? The fourth question is, how to define relationship between two variables? And the last question is, how to apply above concepts in portfolio management? To answer these questions, we have collected monthly returns of a stock as our observations. To begin, we will make 4 basic statements from the dataset. The first point to note is that our dataset has 37 observations. The second point to note is that the maximum value of our dataset is 8%. Third point to note is that the minimum value of our dataset is negative 8%. And the fourth point to note is that the range of our dataset is 16%, which is difference between maximum and minimum value. To summarize, I would say that 37 observations of our dataset range between negative 8% and positive 8%. As a next step, we will structure this dataset by creating frequency distribution to understand how these 37 observations are distributed between negative 8% and positive 8%. Frequency distribution of this observation is done in 3 steps. As a first step, we will define equal and non-overlapping intervals for the full range of our observations from negative 8% to positive 8%. We have created 9 non-overlapping equal intervals with 2% width. These intervals are between negative 1% to positive 1%, positive 1% to positive 3%, positive 3% to positive 5%, positive 5% to positive 7%, and greater and equal to 7%. Similar intervals have been created in left side of the dataset with negative values. As a second step, we will categorize all 37 observations in these intervals. For example, 9 observations are between negative 1% and positive 1%. In similar fashion, we have categorized other observations in the remaining intervals. As a third and final step, we will count the number of observations under each interval. These counts suggest that of the 37 observations, 9 observations are between negative 1% to positive 1%, 7 observations are between positive 1% to positive 3%, 4 observations are between positive 3% to positive 5%, and so on. The distribution of data in such intervals is called frequency distribution, which explains frequency at which data is observed between a particular interval. We could also present this frequency distribution in relative frequency terms. Relative frequency means standardizing number of observations in each interval relative to total number of observations. For example, 9 observations between negative 1% to positive 1% represent 24% of total 37 observations. After creating frequency distribution of monthly return of a stock, we will calculate monthly expected return or mean and the risk associated with that return for our analysis. Mean is the center or average of our 37 observations. Mean to be calculated by dividing sum of all the observations by the total number of observations. The sum of all 37 observations is 0 as number of positive and equal observations are equal. Therefore, the mean of this dataset is 0. Other than mean, median is also an important point of the dataset. Median is the midpoint of the dataset when arranged in ascending or descending order. We note that 0% is the 19th observation, which is the midpoint of all 37 observations. Therefore, the median of this dataset is 0. It should be noted that it is a coincidence that mean and median is the same of a dataset, which is not always the case. Now, another key data point is mode, which is the value that occurs most frequently in the dataset. 0% occurs 5 times in a dataset. Therefore, the mode of this dataset is 0. We should note again that mean is equal to median is equal to mode is again a coincidence, which is not always the case. In real life, the variance between mean, median, and mode is also used in assessing risk, which we will discuss in the later slides. After understanding mean, median, and mode, we will now analyze deviation of 37 observations around mean, which implies deviation from center of the data. The deviation of observations from the mean is analyzed to understand risk. The higher the deviation of observations from the mean, the higher the risk. The question is how to quantify this deviation. First method is to directly calculate variance of each observation from the mean, which is called sum of mean deviation. We note that sum of mean deviation is always 0. This is the case because the sum of variance on left side and the right side of the mean will be similar in values but of opposite signs. Sum of deviation has no utility in quantifying risk as its value is always 0. Second method is to directly calculate variation of each observation from the mean, but in this case take absolute value of deviation of each observation from the mean. This is called mean absolute deviation. In case of mean absolute deviation, sum of deviation on left side and right side of the mean will be similar in value and positive. Another method to calculate variance of each observations from the mean is to calculate square of deviation of each observations from the mean. Add all square of deviation of each observation and then divide the summation by n-1, where n is a number of observation. This is called sample variation and represented by S square or sigma square. Sample variance is a statistical measure of dispersion for a population of n observation. It is to be noted that n-1 is used in the denominator to improve the statistical value of sample variance. Using n instead of n-1 would underestimate sample variance and create biased estimator. Sample variance has a unit which is square that of a mean. Finally, we will take square root of sample variance to bring unit of the deviation to that of the mean. Square root of sample variation is called standard deviation, which is used as a measure of risk. Standard deviation of a 37 observations of monthly return is 3.43%. It should be noted that 23 of the 37 observations means 62% of total observations are between negative sigma and positive sigma of 3.43%. We note that standard deviation of a 37 observation of monthly return is reduced to 2.1% if we decrease dispersion of our observations around the mean. This is what we discussed in the beginning, that higher the dispersion, higher the risk. We often compare risk of two investments. Therefore, to compare two sets of data sets in terms of risk, we standardize standard deviation by dividing it by mean. This is called coefficient of variance. We could further modify calculation for standard deviation as investors are sometimes interested in analyzing risk related to returns below their target return. For this particular purpose, investors calculate target standard deviation. Target standard deviation is calculated by replacing mean with target return of the investor and considering observations which are below the target return. However, it should be noted, denominator remains the same as n-1, even if we don't use all the observations. As a next step, we will further analyze risk by evaluating symmetry and peak nature of our observations defined by skewness and kurtosis respectively. Skewness of data describes symmetry of data on both sides of the mean. The key point to note in the formula for skewness is that it is cubic meter of deviation, which implies it could be either negative, positive, or zero. Skewness is zero when observations are symmetrical on both sides of the mean, as the case with our observation. If skewness is zero, mean is equal to median is equal to mode, as the case with our observation. However, when data has large positive outliers as observation, the center of the data shall move towards right, which implies that mean also move towards the right, in which case mean is 1.4%, median is 0.4%, and mode is 0%. In this scenario, skewness is positive and mean is greater than median, which in turn is greater than mode. However, when the data has large negative outliers as observation, the center of the data shall now move towards left, which implies that means also move towards left. In this case, mean is negative 1.4%, median is negative 0.5%, and mode is 0%. In this scenario, skewness is negative and mean is less than median, which in turn is less than mode. After understanding skewness, we will discuss kurtosis, which measures degree to which distribution is peaked. The key point to note in the formula for kurtosis is of fourth power, which implies it is always positive. Kurtoses are of three types and compare against value of 3. First is mesokurtic kurtosis, for which kurtosis is equal to 3. Second is leptokurtic kurtosis, described as distribution more peaked than a mesokurtic and kurtosis is greater than 3. Third and the last one is platykurtic kurtosis, described as distribution less peaked than a mesokurtic and kurtosis is less than 3. Kurtosis value higher and lower than 3 is called excess kurtosis. Leptokurtic kurtosis has positive excess kurtosis and platykurtic kurtosis has negative excess kurtosis. Our data observation has excess kurtosis of negative 2.97. As a next step, we will define normal distribution, as in real life data is often compared to normal distribution for the analysis purpose. Normal distribution has the following 5 properties. The first property is normal distribution is completely described by mean and standard deviation. Second is normal distribution is symmetric on both sides of the mean with skewness is equal to 0. Third is normal distribution has kurtosis of 3. Fourth property is linear combination of normal distribution is also normally distributed. And the last one is the probabilities of outcome farther away from mean do not get 0. Till now, we have defined distribution of data in statistical terms of mean, standard deviation, skewness, and kurtosis. Our dataset of monthly return of stock is not normal distribution as kurtosis is less than 3. We are in the second last section of our session, in which we will discuss relationship between two variables. We will evaluate whether two variables x and y are positively correlated, negatively correlated, or not correlated. Now, to evaluate relationship between x and y, we will calculate covariance between the two variables. We do not have to get intimidated by this new term. Covariance is calculated by, as a first step, multiply variance of each observation of x and y to their corresponding mean value. As a second step, add all the values calculated from step 1. Finally, divide sum calculated from second step by n-1, where n is the number of observation. It should be noted, covariance has a unit of square, that of a mean. Furthermore, covariance could be positive if two variables move together. However, covariance fails to explain strength of this correlation. Since covariance fails to explain strength of correlation between two variables x and y, we standardize covariance by dividing covariance by standard deviation of x and y. This standardized form of covariance is called correlation, represented by rho. Correlation ranges between -1 and +1. If rho is equal to 0, x and y are not correlated. If correlation is equal to 1, x and y are perfectly correlated. If rho is equal to -1, in that case x and y are perfectly negatively correlated. We are now in the last section of the session. So, let's apply the concept of expected return, covariance, and correlation to calculate expected return, covariance, and correlation for the portfolio. To calculate expected return, covariance, and correlation of a portfolio, we will assume portfolio with 3 stocks A, B, and C with the expected return of RA, RB, and RC respectively, and their weights in the portfolio to be WA, WB, and WC. And the covariance between each pair of stock means between A and B, A and C, and between B and C, and between A and A. Similarly, we should see that at the diagonal of the table, in which covariance of stock A with itself, stock B with itself, and stock C with itself is given. Kindly note, covariance of an observation with itself is a variance, which is square of sigma, means variance. Expected return of a portfolio is expected return on each stock multiplied by weight of each stock in the portfolio. This could also be calculated or expanded to n stocks in a portfolio. Variance of the portfolio is addition of each cell of the below covariance table. Kindly note, each cell in the below table is multiplied by the weights of corresponding stock. Variance of the portfolio with n stocks could be expanded by calculating variance between each pair of stock. In general, in the portfolio of n stocks, n are the number of standard deviations corresponding to each stock, and n multiplied by n-1 divided by 2 are the number of covariance between each pair. The count of covariance could be calculated by using permutation and combination concept, which we have explained in a separate session. Now let's move to standard deviation of a portfolio, which is a square root of variance of a portfolio. With this, we have calculated expected return, standard deviation of a single stock and a portfolio, and relationship between two stocks. Before we close this session, let's go over the key takeaways of the session. First, we have categorized observation over an equal and non-overlapping intervals to create frequency distribution. Second step, we have calculated mean, median, and mode. As a third step, we have assessed the risk by calculating standard deviation, skewness, and kurtosis. As a fourth step, we have defined what is normal distribution. We have also discussed relationship between two variables by defining covariance and correlation, which is ranges between -1 and +1. Finally, we have applied the above concepts of expected return, variance, and standard deviation to the portfolio management. At this point, now we close our session. Thank you for watching this video. Please send your feedback at t2@t2sir.com